So this is a presentation on the work A Low Randomness Second Order AES, and this is joint work with Tim Bijne, myself, Simon Doge, Adriaan Ranea, and Danilo Cicek. And as the title suggests, in this work we are going to create sharings of the AES to protect against side channel analysis, against second order attacks, and we want to use as little randomness as possible. So the question of low randomness AES sharings have already been asked in terms of first order security. Namely, there are two works, Wegner and Morari, and by Sugawara, that have solved this issue for first order security. And both works use the techniques of threshold implementations. And threshold implementations are those that are divided in several layers of Boolean functions. Each Boolean function is walled off by registers, so each Boolean function is calculated over one cycle, and each function needs to be non-complete and uniform. Specifically, uniformity is important because that allows us to reduce the randomness. Now, in AsiaCrypt 2020, Bijne and co-authors created a security analysis to make higher order threshold implementations. So these are threshold implementations that can achieve, for example, second order security. And the idea is quite simple, but it uses linear cryptanalysis. You consider that you have 2 points of information. So you have side channel information from 2 points in the shared cipher. You want to know whether the values that are returned to the adversary follow a uniform distribution or not. In case they follow a uniform distribution, we can conclude that they contain no secret information because the secret information was something chosen by the adversary itself. And we're going to estimate this distribution by taking the Fourier transform of it. And we're going to estimate the coefficients of the Fourier transform by making use of linear cryptanalysis. So basically this boils down to asking, are there trails between probed points in my sharing? Are these trails with high correlation or not? Now we go to the first step of sharing our AES, and that is to share the S box. As mentioned before, uniformity is very important, and it is known that there are no uniform sharings of the AES S box. So we're forced to make use of a technique by Dahmen called the changing of the guards. And in the changing of the guards, it's kind of Feistel-like or more CBC encryption-like. The idea is to take a non-complete sharing, let's call it S bar, to take the inputs to S bar and calculate the output, but to branch off all but one of the shares of the input, and to use input shares from another shared S box and XOR them to the output. You can see that this way, B prime, A prime, and is a permutation with respect to A and B. Now we make slight adjustments to this changing of the guards method because we consider that S bar might not be non-complete. It might instead be probing secure and calculated over several stages. And these stages might also require extra randomness in form of R bar. But then also note that we can get all the randomness out again, and the entire output is still a permutation with respect to the entire input. Now, there is one weakness of the changing of the guards method, and that is that the output size needs to be the same as the input size. For example, here we have 4 output shares, and we also require 4 input shares for this to work. And that means that we can only split the AES inversion over 2 cubic functions, namely x to the power 26 and x to the power 49. To make a non-complete sharing, we need to use 4 shares. Now, that would be a first order non-complete sharing of that S box, but of course you require second order security. So what we're going to do is we're going to take that non-complete sharing, and then divide it over 2 stages. So In the first stage, we're going to have an expansion layer where we're expanding these 4 shares into quite several functions. We're going to add randomness to them, clock them, and then in the next stage, add those shares back together to create 4 output shares again. Of course, this requires randomness, which is what we are trying to avoid in this work. But the idea is that we can reuse this randomness over each S-box. And that is because one particular property of our sharing, and that is that if we even remove this randomness, our sharing from y with respect to x is still first order non-complete. So if we remove that randomness, we still have first order non-completeness. The idea is conceptually simple as if you're placing 2 probes, the first probe might reveal some of that randomness that you are continuously reusing, but the second probe does not learn anything because even without that randomness, you still have first order security. So we are reusing this randomness between S boxes. It's kind of a pay up front type scenario. You pay a lot of randomness, but you can reuse it. And because this expansion layer is quite large, we also investigated ways to optimize this second stage using a custom covering scheme. That's the AES S-box part. But as I mentioned before, for higher order threshold implementations, the diffusion is important. We want our shared cipher to on itself work as a cipher. We want there to be between 2 probed variables either trails with 0 correlation or very, very low correlation. And diffusion there plays an important role. And that brings me to quite a silly slide probably, because everyone is probably familiar with the AES, but recall that the AES has 2 main linear steps. That is a shift rows, which just shifts the cells, and a mix columns, which is in MDS branch number 5 matrix that just mixes the columns. So here we see that the changing of the guards actually changes the diffusion properties of our AES. So remember that the changing of the guards took the input of one shared S-box and actually XORed it with another. And we have to chain all of those S-boxes together. And this creates a pattern, as you can see on the slide. And this pattern actually is a good indication to how the diffusion will change. But note in particular that if I'm going to apply an MDS, so a mixed columns matrix on this row, on this column here, then because I'm XORing just before that the one S box with another, the composition of those 2 operations is no longer MDS. So we suddenly remove this kind of key element property in our cipher. So what we do instead is we take the approach in the middle, which is we're going to chain our S boxes, but only row by row. What I haven't explained is this gray cell here. This gray cell is our extra cell, our memory cell, because after applying our changing of the guards to 16 S boxes, we have to take the output of the last S box, keep it, go to the next round of the AES, and to initiate the changing of the guards of that round, we're going to take that extra cell again to initiate it. And here we see that with this second solution, we need 4 of those extra cells instead of just 1. So that means extra register costs, extra randomness costs, etc. We want to avoid that, but in this case, the improved diffusion is actually worth the extra cost. So this creates this middle layer. However, we're not satisfied enough with that. We actually saw, well, we now have this 4-row, 5-column state, and that actually starts to look a lot like Randall 160. If you remember, Randall 128 is also called AES. So there is a 160 version. And in this 160 version, well, we know that there is good diffusion, so we're going to try and simulate the diffusion as if in Randall 160. We do this by adding an increment to our changing of the guard. So suddenly this input of this S box is XOR to this output, and it continues on. So this input will be XOR to this output, etc. And what we do to top it off is we take this last column and we also apply a mixed columns over this extra column. And this would give us better diffusion, something that's shown in 2 slides. First, I need to tell you what is the property of our sharing that we created, the linear properties of our sharing. We require that our shared S-box also kind of behaves as if an S-box, and that means that the correlation matrix of those shared S-boxes do not have a large value in them. And this is specifically what is said in these claim 1 and 2. Recall that we have split the S-box in 2 cubic parts, x to the power 26 and x to the power 49. We are calling these F and G. And we want that the correlation, the maximum absolute correlation of these sharings is no bigger than 2 to the minus 3 and 2 to the minus 2.6 respectively. We also, because these are not permutations on its own, right? They become permutations because we put them in the changing of the guard structure. We also bounded their non-active to active transitions by, well, 2 to the minus 3.8 and 2 to the minus 4. Now, what we did is we made use of SMT solvers, and the specific SMT solver we used you can find here, in order to program in the sharing that we just created and to find what are the best activity patterns through this sharing. And it's with this tool that we could have tested all this diffusing properties of the changing of the guards that I said 2 slides ago. Here we find the best trail between 2 probes, so between 2 active cells that you can find through the shared cipher. And you'll see that this activates at most 22 S-boxes, if I remember correctly. But note that we made a difference between active to active transitions and non-active to active transitions. And so instead, what we found, so the SMT solver also optimized over this instead, and so we found that the best pattern has absolute linear correlation at most 2 to the minus 55.2. And this brings us to the security claim that you can see before you. It says that the advantage of the adversary is bound by the square root of the number of queries or the number of traces divided by 2 to the 61.4. For people from cryptanalysis, this might seem like a very bad bound, but I want to specifically say that in sideshell analysis, the data given to the adversary is limited to typically 100 million traces. So this is 2 to the 27 traces. So with the limited data amount, this bound actually becomes quite good. So when calculating the previous bounds, we actually found something interesting. We found that when calculating epsilon, which consists of the multiplication between the support of the Fourier transform and the infinity norm of the Fourier transform, which consists of the using piling up the maximum absolute correlation that we have calculated before, and the number of bits viewed by the probes. And from this, we see, well, that we lose 48 bits of security because of the high number of bits that a probe can see. And this is because of glitches. Because of glitches, if I put a probe in the S-box, potentially I can see even 24 different values using just a single probe. And this seemed to us something that was wrong. We didn't believe that in practice you would be able to see in a single trace information from 24 different bits just using a single point in that trace. And so this is where we wanted to sharpen our glitch model using some experimental results. And though experimental results, with that we mean simulation-based results. We made a small change to the glitch model. That is, instead of a probe giving back all values, which was a glitch extend probe in the past, Instead, now the adversary can choose an arbitrary Boolean function of those values, which is a minor change. But it allows us to make theorem 3, and there's a lot of text there, but it basically means to say is that we can make the same estimation as before. However, if we now take specific glitch functions, which are these functions chosen by the adversary, then the bound can be calculated using the L1 norm of those functions. So what we did was we implemented our AES box and we gave the implementation for our simulation. We gave it random delays, we gave it random initial states, random inputs, and we went through all different probe positions. And from that, we started to make the spectrum of what those probes gave back. We did the same for a 9-bit XOR, just to give a perspective of what was happening for a much more simple function. Interesting to see is their L1 norm, and we find that the maximum L1 norm is around 1600, which is around 2 to the 11. So if you recall before, in the original glitch model, it was said that a probe would basically return 2 to the 24 bits of information back. And here we find that on the worst case scenario, you are getting 11 bits of information per probe back in that AES. Also, we find that in our XOR, instead of giving 9 bits of information, because it's a 9-bit XOR, you are getting at most 20, which is around 5 bits information. So this is better than a square root improvement. And so again, the new security claim is the square root of q to the power divided by 2 to the power 88. So this is several times better as before. So in the next part of our work, what we did is we tried to amortize the randomness. And essentially that means that we're going to try and subtract randomness from one sharing of the AES, so one call, and to use it in the next call. And remember that the sharing of our AES has good cryptographic properties. So the sharing of our AES actually works as if it's on itself a cipher. And what we're going to do is we're going to try and use some sort of feed-forward modes of operation. That means that in the picture you see, every branch means that we're going to take 3 out of 4 shares of the state, and we're going to XOR them together. So we XOR the initial state together with the state after the 4th round of our shared AES together with the state of after the 8th round of AES. We add those together to create some random bits that can be used in the next call. So in order to analyze this construction, you got to consider that there are multiple blocks of your shared AES, and you can place 2 probes for each block that is on there. And now you're not just searching for trails between those 2 probes, you're actually searching for trails between the entire construction, which might be a lot better. The bound stays relatively the same, so your epsilon is now the best hull you can find over the entire construction, but it is multiplied by the square root of 2 times the number of blocks minus 1. With this technique, we can amortize away, I believe, half of the randomness. So in total, our construction uses 1,800 bits of randomness. You can amortize away a bit more than 900 bits. But on the new bound, I believe if we were more critical, you would see that our construction is not uniform, so it's not balanced. And that means that the piling up approximation, which was assumed, might actually not hold, and there might actually be multiple trails that just hold together. For the final conclusions, what we did in this work is we looked at this theory from Bana et al. From AsiaCrypt 2020, and we looked at how can we use tricks to save upon randomness, how can we try and share the AES such that it's not using much randomness in the second order case, and we had to tackle the diffusion, the changing of the guards, changing the diffusion of our entire cipher, how to overcome that by looking into what happens when one probe is able to see a lot of bits. Can you somehow still expect practical security? How do you deal with the theoretic model of glitches versus the practical case of glitches. How do you amortize randomness over multiple queries, which can be a really nice tool to remove randomness for any sharing, also first order sharings. And in total, we created an AES where only 840 random bits are needed for the entire sharing. However, the area cost of the sharing is really high, and we actually estimated our S-box to be over 40,000 gates big. And this is the same wall that was faced by Wegner and Morari, and this was the wall that was solved by the work from Sugawara, where the AES S-box was divided over several quadratic functions. However, this trick was not used or usable because applying the changing of the guards multiple times over one round of the AES would only dilute the diffusion even more. And already we had quite bad diffusion. So how to overcome this weakness of the changing of the guards versus a much more efficient sharing is an open problem that we still pose with this work. And with this, I thank you for your attention.